So let's just start with a trunk. So I'm starting just with one little line. How many lines do I have here? One, right? So in level 1, there's 1. Okay? And then what does it say to do after the trunk? How many? 2 branches. It splits off into 2 branches. So now, how many new branches do we have in level 2? 2. Okay, and then what happens after I split into 2 branches? Now what? Yeah, each one splits into 2 more. So now how many?
Uh-oh. I
don't think you did anything. So how many new branches are there? 4. And then I want you to keep going. Split them up again. And record how many new branches are there in each level. If you want to use colors, you may use colors, but I want you to see what level can you get to? What level can you get to? I'd like to see you get to 9. Bless you. Did anybody draw all the way to level 9? I don't know, is it? Did anybody draw to level 9? You got to level 7. Did anyone get to level 8? Not yet. Has anyone given up already? Yeah? Yeah, I'm going to give up after this one, I think. I don't want to spend all of class drawing little lines. But did you figure out the pattern? Huh? What's the pattern? Yeah, keep multiplying by 2. So can you help me out? Can we fill this table out, please? How many would there be at level 4? That's the light blue. 8. And at level 5. And at level 6. And at level 7. And level 8. 128. And level 9. 256. Very good. And like you just said, right, we're just multiplying by 2 every level, right? So every level, the number of branches doubles. Doubles, let me just say every level. Does this remind you of anything?
A tree.
A tree, obviously, right? It's the magical math tree. What else? What else does it remind you of? Anything? Huh? Broccoli. Yeah. Yeah, it looks like broccoli.
Something in science.
Yeah, that's what I think about is like veins. You know, you look at like the veins in your eyes or veins. I don't know. That's what I think of. Veins. What did you say, Connor? An atom? Or synapses in your brain. That's really cool. Yeah, or like your nerves, your nervous system. That's good. Anything else? No? Huh? Does it remind you of anything else? Does this remind you of anything?
No.
Not a single thing? Huh? A tree. I already said a tree. Ooh, electricity, like lightning. Yeah. I think of like a river as well. I think it looks like a river. You know, rivers like split off into little branches.
And what about the weeds that you blow?
Oh, yeah, 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 yeah. Uh-huh, like dandelions.
Is that what those are?
I think so, yeah. Yeah. Good. Cool.
Chicken feet.
Chicken feet. All right. Okay, can we look back at this table? Let's look at this table. And we said we're just multiplying by 2 every single time, right? Multiplying by 2 every single time. So I got 4 because I just took the previous 2 and then just multiplied it by 2, correct? And I got 8 because I took the previous 4 and I multiplied it by 2 again, right? But that previous 4 was also just 2 times 2, right? And then 16, I took the previous 8, or the 2 times 2 times 2, and I just multiplied it by 2 again, right? So it's what?
Exponent?
It's exponent. So how do I write 16 with exponents?
Or no, 16.
How can I write 16? How can I rewrite 16 using exponents?
2 and 4 over it?
That's it. 2 to the 4th power. What about 8? How do I write 8? 2 to the 3rd. What about 4? 2 to the 2. How do you think I write 32? How do I write 64? And 128? And 256? Can you guys cut it out? Keep your feet and your hands to yourself. How do I write 2 using exponents? How do I write 2 using exponents? Not 2 to the 0. 2 to the 1st power. How do I write 1? 2 to the 0. 2 to the 0, good. So look at our level numbers. Look at the levels and look at the exponents. What do you notice about the relationship between the level we're on and the exponent we use? What do you notice about the level we're on?
One, like their 1 is 0, and level 2 is 1.
Yeah. So how would you explain that? You're right, Jaden, but I just want how much further ahead? So it's 1 more or less?
More.
Yeah, right? The level is 1 more than the exponent that we're using, or the exponent is 1 less than the level that we're on. Good. So if I'm at level 1, right, I take 2. 2 is always my base. And my exponent is going to be 1 minus 1, so 0. When I'm on level 2, my base is still 2, but I'm raising it to the exponent of 2 minus 1, so 2 to the first. In level 3, my base is 2, and I raise it to the exponent 3 minus 1, so 2. So if I want to write an equation that represents the number of branches at level n, what would I need to do? What is the equation to represent the number of branches for level n? Not level 1, not level 2, not level 8, not level 9, but level n. What would it be? What's going to be my base? No. What was my base? 2. And then what did I do to figure out my exponent? Subtracted by what? Subtracted by 1, so I'm going to just do 2 to the n minus 1. And that's my equation to represent this relationship. Okay, so can we figure out how many branches there's going to be at level 15?
Yeah.
How? Just keep multiplying by 2, that's fine. Yeah. 2, how did you get to the 14th power? Yeah, we're subtracting, right? This level 15, that's my value for n. So this becomes 2 to the 15 minus 1, which is just 2 to the 14th, which is what? Put that in your calculator.
16,384.
Good. Okay. Let's look at the other side. Let's look at the other side. What's on your shirt? Something you shouldn't have on. Okay, so now we're looking at zombies. There's a zombie outbreak, and there's 2 different types of zombies. The first one is strain A, and the second one is going to be strain B. Strain A, how many zombies are we starting with? Yeah, 1 zombie. And each day that original zombie infects 2 new people. So on the first day, it's going to find 2 people to infect. And now how many total infected people are there? 3. The newly infected zombies can't infect new people, only the original zombie. So on the next day, it infects 2 more people. So how many total are there? 5. And then the next day, again, the original zombie infects 2 more people. So how many are there? Right? And again, the next day, the original zombie infects 2 more people. So how many are there? Do I have to keep drawing? I do? We know, yeah, what's the pattern? Right? It's going up by 2 every single time. We're adding 2. So how many will there be on day 5? And on day 6? And on day 7? And day 8? Very good. Okay. Okay, now let's look at strain B. So how many zombies are we starting with strain B? Huh? 1. Starting with 1 zombie, but this strain, each day, every zombie infects 2 new people. So on day 1, this zombie is going to infect 2 new people. How many are there total? Is it any different than the other one? No, not yet. But then the next day, every zombie infects 2 more. So how many total zombies are there now? 9. 9, right? I have 3, 6, 9. And then the next day, each zombie infects 2 more people. Mm-hmm. How many are there now? Not 81. Not there yet. Not 22. No, not 11. Look. 3, 6, 9, 12, 15, 18, 21, 24, 27. So there's 27 on the 3rd day. Are you going to make me keep drawing this out, or do you think you can figure out the pattern? Draw it. You draw it, Zell. Exactly. We're multiplying by 3 every single time. Multiplying by 3. So how many would there be on day 4? 81. And on day 5? And on day 6? And on day 7? Very good. And on day 8? Perfect. Good. Okay, so can we do a little compare and contrast here? Compare, contrast. So tell me, what's the same about these two? Good, they both start with 1 and then 3. What else? What else is the same about them? Yeah. Yeah, that like 2 new people each day. What else? What else is the same about those two? Are there more zombies at the end or less zombies at the end? In both of them or just one? So then they're both increasing. Both increasing. Okay, now let's look at what's different about them. What's different about these two? Good. One is adding and one is multiplying. Right. So A is adding, and yeah, they're different colors. B is multiplying. Which strain would you rather encounter? Which zombie strain would you rather encounter? A. Why A? Because there's less of them, right? It would be much easier to take on like 17 zombies than take on 6,561 of them, right? But what if this wasn't zombies? What if it was like money in your bank account? Yeah, you'd rather have B, wouldn't you? Rather have more money than less money. I'd rather have $6 grand than $17, right? What if instead of it being money in your bank account, what if it was like money that you had in debt? Right? I'd rather have A as well, right? So that's why we're looking at exponential equations, because they show up all over the place, right? They show up in nature, like, right? You can look at that tree and see like a magical math tree, right? The trunk splits into branches, which splits into branches, which splits into branches, right? And gets more and more and more and more. It also shows up in, I mean, we haven't had a zombie apocalypse yet, but like any type of infectious disease, like COVID, right? It became such a big deal because that spreads exponentially. It's not that just one person infected one person at a time. It was that one person infected 25 people, and each of those 25 people infected 25 more people. That's why sicknesses spread so quickly, right? Same thing with money. Again, so you can keep money if you do have like a little bank, a little piggy bank at home, and you're putting $20 in every month or every week or whatever, it's growing like this because it's only going up by a fixed amount every single time you put it in. But then if you have something like a high yield savings account, or you eventually go on to invest your money, that money grows exponentially. It uses percentages, and there's a rate that it grows by. So it can grow more and more and more. And, just like there's two sides to every coin, right? That can help you out when you're saving money, but it also works that way when we take out loans. And that's why I had you guys look for the houses the other day. So we're going to look at a mortgage loan and how, even though you might buy your house for $180,000, over the 30 years of your mortgage, you'll probably end up spending $400,000 on that house, right? That's how car loans work. That's how credit card debt works, right? You can go and when you guys turn 18, I'm sure you will start receiving advertisements for credit cards, and you can apply for a credit card, and you will go to Walmart and you could just buy a brand new iPhone. You don't need to work for it. You don't need to pay anything of your own money, right? But if you put that on your credit card, right, it might cost you $1,000, but there's a 25% interest rate on that credit card. So every single month, that $1,000 turns into $1,050 and $1,100 and $1,300 and $1,500. And if you ignore that for a whole year, you're going to end up spending twice as much money as what it actually cost, right? And so again, that's why we're looking at exponential rates, because there's a lot of applications. Okay, let's look at these on a graph now. What time do we get out? 3:10. Okay, we're doing good. Oh, sorry, 2:15. Okay, even better. Okay, let's look at this. So I know on your paper it's kind of hard to see, but do your best. There's, on the x-axis, we want to put the days. So there's like kind of thicker lines. We're going to count by twos. So 2, 4, 6, 8. And then in between, we want 1, 3, 5, 7. And then along the y-axis, we're going to put the number of zombies. And on these thick lines, we're going to count by 5. So 5, 10, 15, 20. And remind me, how many zombies were there on day 0 for strain A? 1. Right there. And on day 1, how many were there? 3. And on day 2, how many were there? Huh? 5. On day 3, there's 7. On day 4, there's 9. On day 5, there's 11. Day 6, there's 13. On day 7, there's 15. And on day 8, we had 17. So what do you notice about this graph? What do you notice about the graph? Yeah, there is a constant, good, a constant rate. Very good. Do you think that constant rate, is it positive or is it negative? Yeah, it's positive. And how did you know that? Good, because it's increasing. Very good. What's the shape of the graph? What's the shape? Whoa. What was that? Is that a little firecracker? Oh.
Trying to get out of here was quick backwards, like, get out of the way, Miss Terry, make another doors in the window.
You guys, what is the shape of this graph?
Square.
It's a line.
The graph is square. It's actually a 90 degree.
Linear. Well, that's the coordinate plane, yes. But the graph is just this. So the line. So this is a linear equation. Could we write an equation for this graph? Yes, you can. Do you know what form to write it in?
Y equals M.
Good. What does M tell us?
Slope.
The slope. And what does B tell us? Y-intercept. What is the y-intercept of this line?
0.
No. Yes. And what about my slope? What is the slope of this line? Up 2 over 1. Up 2 over 1. Up 2 over 1, right?
What?
What's wrong? What's up? Are you writing this down? You should write this down. You have y equals 2x plus 1 written down on your paper? That's what I thought. Okay. So that's a linear relationship. Now let's look at this. Hold on. Linear. Whoa. So now let's look at strain B. Strain B. So on our x-axis, we're going to count the same way, 2, 4, 6, 8. And we can count in between 1, 3, 5, 7. And then on the y-axis, we're going to count up by 20. So 20, 40, 60, 80, 100. Huh? It's 100. Strand B. It goes up to over 6,000, doesn't it? We're not going to show the whole graph. We're just going to show part of it. How many zombies are there on the 0th day? 1, right? So that's like down here. And on day 1? Yeah, there's 3. On day 2? Does this look very different at this part? It looks a little different. Does it look like really different? Just a little bit different, right? It's a little lower, yeah. What about on day 3? How many are there? 27. What about on day 4? Now does it look different? What's this shape? Yeah, it's kind of like a U. I guess like half a U, right? Good. But is it a linear graph? Is it a straight line? No, it's non-linear. Non-linear because it curves. But is it increasing? Yeah, still increasing. And do you think I can write an equation for this?
No.
You don't think so?
Maybe.
Do you think I would write it in this same format?
No.
Definitely not. So let me show you. This is kind of the like general template when we're looking at an exponential function. An exponential. So y equals a times b to the x, where a is the starting amount, and b is what we call the growth rate, or the growth factor. Growth rate. So what is the starting amount for strain B?
1.
1. What are you doing? And what is the growth rate? What are we growing by each time? Times 3. So 1 times 3 to the x. And that's our equation. We need to upload this other part. We're going to do that other half of the paper now.
Oh my gosh, I forgot.
So strain A is an example of an arithmetic sequence. An arithmetic sequence. Thank you. Strain A is an arithmetic sequence. And arithmetic sequences have what's called a common difference. Oops. And a common difference means that we add to go from term to term. Add the same number to go from term to one term to the next. And arithmetic sequences produce linear relationships. So let's look at some examples of linear growth. Linear sequences, arithmetic sequences. So in this first one, I'm going from 3 to 5, 5 to 7, 7 to 9, 9 to 11, 11 to 13. What is my common difference? Yeah, we're adding 2, so my common difference is just 2. And what would the next term be? 15. Very good. Okay, the next one, same deal. Going from 9 to 5, 5 to 1, 1 to -3, -3 to -7. What am I doing to go from term to term? Subtract first. What's my common difference? Negative 4. Negative 4. So what would the next term be? Very good. Negative 11. Okay. What about the next one? Negative 10 to 0, 0 to 10, 10 to 20, 20 to 30, 30 to 40. Yeah, my common difference is 10. And what would the next term be? 50. Very good. Is this first one, is it increasing or decreasing? Increasing. And did it have a positive or a negative common difference?
Positive.
Positive common difference. And what about this one, the second one? It's decreasing. And did it have a positive or negative? Negative, right? So it's just kind of like slope, right? When I have a positive slope, I have an increasing line. When I have a negative slope, it's a decreasing line. Okay, and then let's look at strain B. Strain B is an example of a geometric sequence. Geometric sequence. Geometric sequences don't have common differences, they have common ratios. Which means that we multiply to go from term to term. And geometric sequences don't produce linear relationships, they produce exponential relationships. I have music on. And I have my air purifier thing going. Okay, let's look at these examples then. So I have this first sequence 3 to 6, 6 to 12, 12 to 24, 24 to 48. What's my common ratio? What am I doing to go from term to term? Multiplying by 2. So my common ratio is 2, and what would my next term be? Mm-hmm.
Can Tristan Jones please come to the front office? Tristan Jones.
What about the next one? 2 to 6, 6 to 18, 18 to 54, 54 to 162. What are we doing? Good, multiplying by 3. How did you know we were multiplying by 3? And 6 times 3 is 18. And then I'd guess you probably don't have your 18s memorized or the 54s memorized, do you? No. But is there a way we could figure out what our common ratio is in case we don't know what we're multiplying by?
Yeah.
How? What's the opposite of multiplying? Dividing, right? So I can take any number from this list, and if I divide it by the previous number, divide it by the one right before it, I'm going to get that common ratio. So can you guys do that? What's 162 divided by 54? Use your calculator. 162 divided by 54 is what? And 54 divided by 18 is? And 18 divided by 6 is? And 6 divided by 2 is? Right? So that's how we find our common ratio if we don't know. And then what would be the next term in this sequence? 486? Yeah. Okay, so can you guys try this next one? 27, 9, 3, 1, 1/3, 1/9. Take one number and divide it by the previous number. Take one number divided by the previous number. Take one number divided by the previous number. Doesn't matter which ones. You should always get the same thing. What do you get when you divide? What do you get? 0.33333. If you take 27 and divide it by 9, you're going to get 3. But you need to go backwards. So 9 divided by 27, it gives us 0.3 repeating. How do I change that into a fraction? No. How do you change it into a fraction on your calculator? Math, enter, enter. Can you do that? 9 divided by 27, math, enter, enter. What? Not 3/10, no. 1/3. So that's our common ratio is 1/3.
Oh, you're not smart.
And what would the next term be? Very good, 1/27. Which ones, okay, so there's sequence 1, sequence 2, sequence 3. Which ones were increasing? Yeah, these two were increasing, right? And what about the third one? Decreasing. Right? So when I have a common ratio that's greater than 1, my sequence is going to increase. If my common ratio is less than 1, then it's going to decrease. Right? When it's a fraction, I'll see it getting smaller and smaller. Can you guys try and do these practice problems? I don't expect you to get through all of them in 5 minutes, but I want you to try. See what you can get through. They're just like these ones. They're all geometric sequences. So find the common ratio in the next term. Remember, you can find the common ratio by taking one number and dividing it by the previous number. Okay? Let me see what you can come up with. Oh, you got an old one. I thought I threw them all away. Use this one on your desk. You got them there? It's okay, you can.
So what, this is one?
Yes.
Let's get 3.
This is just, gonna do.
There's 8. It is. Daniel?
Where do you see two negatives? That's one negative. So those negatives. Is it 1/4? Right.
We're going to take this last number and multiply it by this.
Yes, she did. That's what I'm sure. You have to do this.
So then you can
On top.
go say,
Yes, a question.
so it needs to be multiplication.
Oh, no, she just.
So yes, you're dividing by this, but we're multiplying by
Yes. Yeah, like one times yeah. What do you do? It's so low. Well, parking spot. Oh, you think it's gonna be up? I know, every time it goes back, I go down. 8 seconds later. It's loud. It's crazy because everyone gets quiet. It doesn't matter when it's just always happening.
Gotta grind on that class.
Yeah. He's gonna shoot today. Had it for home now. Yeah, just put it in Anthony.
Don't hit me. What are we even doing today?
Just finish watching that video, and then you have like some cards to do, but it's super easy.
So during the video you wanna play?
Yeah, man.
Yeah.
Gotta get the last.
Anthony, I'll press this.
Mia, look at yours.
Yes, I literally lost sleep all day. It's so sad.
Yeah, it was. I didn't notice it until seventh period yesterday, and I assumed it was yours, but I wasn't sure, and I was like, well, she'll come back if she was looking for it. So